Hello and welcome to a discussion on Module 4, which centers on Spark in big data. Jumping into what's it about. And the basic idea is that we're talking about kind of the next generation of big data technologies, right? So far in this course we've talked about things like MapReduce and Hadoop and Hive. This is kind of the natural evolution of things, which is now to talk about Spark. So by the end of this, you'll have some basic idea of this module. You have a basic idea of data manipulation problems that you can do with Spark. The materials in the course are a little confusing on terminology, so I'll try to clarify that somewhat. Apache Spark is the project that we're talking about here. Scala is a programming language that Spark supports. It also supports some other languages, and we'll talk about that in a little bit. The course designers were a little loose with the terminology. So you do need to understand the concepts of functional programming, that it's essentially kind of, in a sense, declarative, that you're saying what you want to happen, and then Spark figures out how to do it. And then you need to understand the concepts of resilient distributed data sets, which is the foundations for Apache Spark. It's kind of the thing that makes Spark do what it does. And then there's also this concept of filtering, of something that we typically do quite a bit whenever we're doing data manipulation. So jumping into kind of the basic question you always want to ask yourself is, what is it? So what is Spark? And the short answer is it is a unified platform that is optimized for processing. Unified in the sense that it takes care of pretty much all of your big data sort of needs. You can do things that you might traditionally have done with Hive, because it oftentimes utilizes Hive. It can also be used for stream processing and batch processing, and all in the same sort of way. The stream processing it does isn't necessarily 100% true stream processing, in that the arrival of an item in a queue doesn't trigger processing. Rather, Spark uses this concept of micro batches. So why would you use it? Well, it's up to 100 times faster than Hadoop's MapReduce. And that's not a typo, 100% faster. And the reason for that is that in general, Spark is optimized for memory processing. So if it can keep the data in memory across the cluster, that's when you see that 100% times faster. If it has to spill to disk, which it can handle, it's not a memory-only processing, so it can do disk-based processing as well. It's still going to be significantly faster than MapReduce, in the order of magnitude of at least 10 times faster, so at least one order of magnitude faster. You use Spark for a lot of things, including data wrangling and processing. You may do it for analytics, and you may do stream processing as well. So it's a lot of things that historically might have been attempted to do using MapReduce, something that Spark uses instead. So the key concepts to understand, first of all, I hinted at it earlier, RDD, so the Resilient Distributed Data Set. That is the foundation of Spark. It is kind of what makes it work. And it's strongly typed, so that there are data types associated with things. And it keeps track of what's been done to the data by the various operations that are needed, so that if need be, it can be redone if one of those nodes in the cluster goes away. It also is transformational in nature. You don't really change a data set itself. Rather, you construct a new one from an existing one, or potentially by reading something off of either disk or stream or memory or whatever it may be. And they are partitioned across the cluster. That's a key concept as well, so that ideally in a relatively even sort of distribution, so that the various workers in the cluster can have an equal share to pull. An example of running a program inside of Spark is to potentially do it from inside of SQL. So there is a Spark SQL that is pretty close to Hive, and it allows you to essentially do things that you might normally do in SQL. So you can create a table, you can populate it, and then you may potentially delete it and update it and various other things. We'll see that in a little bit more in a moment. Structured streaming is also important to understand, and it's like I mentioned, it's done through micro batches rather than true stream processing. The way that works is that when stuff goes into essentially a queue to be processed, every so often, and it's configurable, Spark will wake up, essentially run a job, and then kind of essentially put it kind of back to sleep. So unlike batch processing where the actual process terminates, it's more of something with a long sleep in it is the best way to think about it. And the way that Spark kind of treats the whole concept of a stream is essentially an unbounded table. All that means is that it's a table that potentially keeps getting larger over time. New rows are continually being added to it, and you can process, depending upon what you want to do, only those new rows. There's also this concept of a temporal window that you may be applying so that you may be doing something like aggregation over a certain amount of time. So you may be doing a group by or whatever it might be. And you can kind of see the kind of the concept there of the micro batch sort of architecture in the image in the middle, where a trigger occurs and you don't do anything to make this happen. It's something that Spark takes care of for you. And maybe it happens every second. It wakes up, it looks for something to do, and then it essentially outputs the results. You have different types of modes of output. You may want to only do essentially updates to things. You may want to output the entire contents, so that's what the complete mode might be. And you can potentially do something here such as like a word count, right, which is what the rightmost window is looking like. Another key concept that's relative and related to Spark is MLlib. That is a machine learning library, as the name kind of implies. It lets you do a lot of distributed machine learning algorithms. So rather than doing stuff all on a single computer, you can distribute the workload across a cluster and do machine learning on machine learning optimized hardware, potentially, including things like GPUs. And they allow you to do things like feature extraction, classification, regression clustering, recommendation, and so on, all the good stuff that we normally do inside of machine learning at scale. And that's the key concept. It's about doing it potentially at large volumes. There's also things like a cross validator that lets you do things in tuning, and then there's also some things that we may get into later where it'll actually, one of the key companies that's embraced Spark has recently released, or relatively recently, AutoML, that essentially does AutoML sort of operations by essentially doing all of the types of stuff that a typical developer might do, and doing it to produce a result based upon picking which one is the best of those models that are being generated based upon some criteria that's established by the developer. You can see here also that this is the Scala version of the implementation. That's another one of the languages that Spark supports, is Scala, in addition to SQL and Python. And you can even do it in Java if you're so inclined, although it's a little more painful. Graphics is also something that might be relevant, although it's less so. And there's also the concept of graph frames. The idea is that there are mathematical graphs, and we'll talk about those in a moment, that are a way of representing relationships between things in a nodes and edges sort of approach, so that you have a relationship between things, the relationship and the things themselves, so the edges and the vertexes or vertices can all have properties associated with them, multiple properties. So in this situation, sometimes the connection is actually as important or more important than the actual nodes that are being connected. And again, this is some Scala code that's basically showing the creation of a graph. And then potentially you can then do graph algorithms on it, such as things like PageRank and so on. So with that, we'll jump over and actually show you an online hosted version called Databricks. And I'll start here. You can sign up for free. It doesn't cost you anything. And let's see if we can get in here. But once you've logged in, you'll see an interface pretty much like this. The whole point of the community edition of Databricks, and it's simply community.cloud.databricks.com, is to let you learn about Spark in an easy and accessible sort of way. Databricks is a company that was created by the founders of the Spark project. And they basically decided that the thing that they had came up with while they were working at Berkeley was good enough that maybe it should be shared at a commercial level. And so Databricks was created as a company to utilize Spark and bring it to the masses. It was interesting because it was a cloud-only company, and still is. So there's not a implementation of it that you install locally. Generally speaking, there might be exceptions, but as a general rule, there's not. And so the idea is to take something that is really powerful and compelling, like Spark, and then put a nice front end in front of it, such as a notebook interface, not dissimilar from Jupyter. So very, very similar sort of user experience, and then making it really easy to do things like create a cluster and basically scale your workloads depending upon what you need to do. So the UI, pretty straightforward and relatively clear. Starts off with the kind of the home up here with the Databricks logo, and it's also got a auto expand sort of thing going on, which you can turn on or off depending upon what you like. There's some different personas they've created now, which right now in the community edition, it's only the data science and engineering and the machine learning sort of personas. The idea is that depending upon who the user is, they may want a different set of functionality. And the machine learning is where the AutoML is at. There's a create, which basically gives you the choice of creating various things that you might typically want to do, notebook, tables, or clusters. And there's also this concept of a workspace, which is kind of like a directory that is can be, if you're in the non-community edition, shared across multiple users, and you can actually collaboratively edit a notebook at the same time. So two people can be in the same notebook at the same time, seeing what each other is doing. The home page is nice in that it kind of shows you typically the things that you've recently done or the things that you might want to do, including creating a cluster. There's ability to search across the workspace. You can see the things you've recently done. And then there's a data tab, which basically allows you to look at the data that exists inside of your workspace, very similar to what you might do from a database perspective. And then jobs is nothing more than a scheduled notebook, not something that you necessarily would do in the community edition, but in the versions that you can get through AWS, GCP, or Azure. You can certainly schedule a notebook to run at a certain cadence. And then there's some other stuff in through here, settings and so on. But generally, those are the pieces you're most interested in. Jumping into a notebook here, and also to just talk through the homepage, there's the common tasks, a quick start tutorial, and then a quick start notebook here that's using SQL to get going. Probably the same basic thing. Yes, that's the same thing. So the first thing that you typically want to keep in mind is you need to have a cluster created or running. I started it before this class, so we can go and make sure that it's actually truly running and up and alive. And so what this is doing is running an SQL command, and we know it's SQL because the default language for this notebook is SQL. And what that means when I'm saying default language is you can actually have multiple languages inside of the same notebook. So you can switch between whatever language makes the most sense based upon what you're doing. There are a few sort of caveats you have to keep in mind. You can't declare like a variable in Python and think it's going to work in SQL. However, you can do things like create temporary views or tables and cross those across the process boundaries. What this is doing is creating an external table at this location. So there's a path inside of the data sets that exists for pretty much everybody, a read-only path. That is the diamonds data set, and it does have a header. And so after having done that, we can do a select on it and see the values that are inside of that table, just like you would in Hive or just plain old SQL. And you can see that they are what you would expect. There's also some interesting characteristics inside of Databricks that might be useful, might not. You can do things like create bar graphs by or whatever type of graph you might want, and you can actually go through and change the options. So you can change the plot so that maybe you only want to see probably not X and Y, but maybe you care about caret. I'm not sure that would do much, but we can see what happens. Probably need to switch that over to a histogram, perhaps. I guess it was a histogram. The point being, you can definitely do beyond just a grid exploration and actually be able to see more sort of simple data exploration. It's not fantastic, but and it's not going to be something comparable to like Tableau or Power BI, but it's not a bad sort of way of taking a look at the data. This is another way of constructing a data set, and what this is doing is actually, and you can see here crossing language boundaries here. This is switching over to Python, and we're reading a CSV, which is the same CSV we just read. This time we're telling it to infer the schema as well as that there are headers, and then we're going to turn around and create a delta table in this workspace or a delta format inside of the file system inside of here. So all this is doing is basically writing it out as a delta table format. It's not delta yet, but it is the delta format. Delta is nothing more than a Parquet file plus the ability to do some journaling. What the reason why you would want to use it is that it also brings ACID compliance to the big data world, something that doesn't exist. So if halfway through a process something happens and it doesn't complete successfully, it's an all or nothing proposition within that context. It's not a true transaction per se, but it is atomic in nature so that you're assured if something will succeed or fail. It's not transactional in the sense of like a multi-table update inside of a database, but it is something that makes sure that you don't have a partially applied sort of merge or insert. And here what we're doing is dropping the table that we just created up here that was named diamonds. We're replacing it now with a delta table that's running against that delta file format that we just wrote. Similar experience, so we can do selects. The things that delta also does for you is helps with some of the traditionally painful big data problems. So there's a problem known as the small files problem inside of the big data world. All that really means is that most of your big data technologies do very, very poorly if you give them a bunch of little files. Rather, they do well whenever it's a few big ones. And the size of what is good and not good, sometimes it's best to let Databricks and Delta figure out. Delta is an open source offering. Let's see if this works. Is it that maybe? Yes, optimize. And what this does, optimize goes through and it takes care of that small file problem and basically merges things together for you. So it's some of the maintenance that you might do on your data lake and your Delta Lake, similar to what you do with a database. So here's an example, a better one of using the graph sort of output that the Databricks interface lets you do. And we can see the distribution based upon the quality or the color and the price, right? So corresponding that the things that are the highest color, J, is also the highest price, which is what you should hope. If you click on this, you can switch over to a table versus the graph. So it's the same data, you're just how you're viewing it. Then you can also just download it if you were so inclined. That basically just downloads the CSV for you. So it's easy enough to get. If there's more than a certain number of records, you may have a prompt that asks, do you want to rerun it and get back everything? It'll give you up to 1 million records, so there is some limits there. Here's an example of reading reading the diamonds into a CSV data frame. And then basically here, you're doing this from inside of the PySpark approach. So rather than going through an SQL query, we're going through a data frame called diamonds that we've loaded. It's not a table. This is a data frame similar to a pandas data frame, except it handles the distributed and it's laying on top of that RDD that we talked about. And it's basically showing you that this is kind of the same sort of syntax. The key thing to understand with Spark and Databricks is that the language that you write your code in doesn't really matter. And the reason it doesn't really matter is because this goes through an optimizer and it figures out what you should do. And you can actually kind of poke into what it's doing under the covers by taking a look at the execution. So you can actually see what it did, including there is this DAG that is created, so a directed acyclic graph that gets created that is basically the Python or the SQL or the Scala is essentially parsed and turned into a DAG, and then the DAG is used to determine what actually happens. So the optimizer can take a look at the DAG and figure out if there's some optimizations that can be done to improve the performance. So there are some interesting sort of characteristics that allow you to tune and tweak your performance when you get beyond something of group by and average, right? So that's kind of an intro very quickly. Also note there is Markdown in here. So the way that Databricks handles Markdown is unlike Jupyter, where you'll go and switch the type of the cell to be either code or Markdown. You start with these magic words. So %MD and %Python are magic strings. The %MD says that what's inside of the cell after that, and these strings have to start at the very beginning. They have to be in line 1 of a cell. But once you see that, it then allows you to embed Markdown, including things like images, movies, whatever it might be, animated videos, whatever, into your cell. And the idea is that it takes that concept of a notebook to kind of another step, right? So that not only is the notebook and the results of the notebook kind of commingled together in an exploratory sort of way, you can turn around and schedule your notebooks when you're said and done to turn them into production pipelines. There's also the ability to do flow control between notebooks if you're so inclined. It uses the concept of a widget, which essentially allows you to have parameters to your notebooks so that you can essentially have one notebook call another notebook, passing in a series of things that control the behavior of that notebook. This allows you to have a much better code base and a better utilization of your resources. Rather than having 1,000 different notebooks, you might only have 1 or 2, but one of them calls the other with the parameters that adjust to whatever it is that particular workload is about. So with that, we've kind of had a brief introduction into a notebook. I'll show you another kind of cool thing here, which is dropping some data. So I've got an example we'll go through. It's a little bit of an advanced example because it talks about graph databases, but at the same time there's some interesting stuff that we do along the way that you might enjoy. If you drag a CSV onto this thing that says drop files or click to browse, it knows that I want to create a table, and it knows that it's a CSV, and I have a choice of either creating a notebook or creating a table with the UI. I'll do the UI just because it's a little easier. You start off picking a cluster. You have to have a cluster running to do this, and then the next thing it does is preview the table. We know that the first row is the header, and we also want to infer the schema. Because I've done this before, it thinks there's more than one, so it thinks that we may potentially have a collision. But I'm going to create a table called edges. A database is essentially like a schema in a lot of databases, to where you can segregate tables based upon whatever use function or whatever they might be, or levels of refinement. So I'll go ahead and click on Create Table. Sometimes it worked this time. Sometimes the Community Edition has a little bit of a hiccup here, but we just created a table and named default.edges. And we can see the schema has got a from, to, and relationship. So these are the edges in a graph, and that would be, you go from one node to another, right? And then there's some sort of an attribute on it called string, called relationship type, which is a string. And we can see here what a little bit of the data looks like. So doing that again, I'm going to import in the vertices now, because we just pulled in the edges. Now we'll pull in the vertices. Again, actually this time we'll go through and do it in the notebook just to show you the different thing. What this does is basically takes that same sort of code that probably happened automatically and lets you see the notebook, and then you can edit it. So we do want to infer the schema, and we do want the first row to be a header. I'm just setting some parameters here that get passed into this function. I want to create a table, or a temp table named temp, and then I want to create a permanent table out here called vertices, and I have to uncomment this because a lot of times you may not want to create, and I didn't need to fix this so that it will work. So a temp table is kind of what the name implies. It exists for the life of the session. So here we can go ahead and start stepping through this. We're going to go ahead and attach to the cluster and run that first cell. And what this is doing is reading using spark.read.format, which is a CSV, we're saying that we want to infer the schema with an option. We want that with the first row is there is a header, and the limiter is a comma. And then it's at this location up here where we stored it. This is inside of Databricks' file system, similar to HDFS, but it is kind of its own kind of variation. And we can see here it displayed the data frame. So at this point, we've just got a data frame similar to a Pandas data frame in memory. We haven't actually done anything with it. And in fact, until you call something that makes it happen, like display, this first line doesn't really do anything. This doesn't really do anything until the results of that instruction are needed. And that's part of how that lazy evaluation essentially is part of how you get real performance benefits with Spark, because it can figure out over time what it is you're trying to do. So it becomes much more about the function that you're trying to accomplish rather than you being very explicit. So what I just did here was take this data frame and say I want to create a temp view, and I give it a name. Temp views, like I said, go away at the end of the session, but we can do a select off of it right now and see what's inside of it. And here we can see there's a node ID, a type, a name, and a label. And as you can see, this has something to do with classes in school. And so now I'm going to go ahead and create that permanent table, and I'm going to call it vertices. And what this is doing is taking that same data frame we loaded up first thing, writing it as a Parquet table with that name. So it's making it to where it persists, and we're actually kind of putting it as a managed table. Maybe not the best thing to do in a production world, but it's okay in a demo. And the main difference between managed and unmanaged is similar to what it is in Hive. If I drop the table and it's a managed table, the data is gone. If it's an unmanaged table, I basically have a table that's pointing at external data, and dropping the table doesn't affect that data. So in a production world, that's typically what you want to do. So here's an example notebook, and I'll go ahead and clear results. Hopefully that'll get rid of this. All right. So I start off by showing, in part, what is a graph and a mathematical graph we've kind of talked about before, but the basic idea here is that it's around an edge between two nodes, generally speaking. So, and in particular, oftentimes that edge is directed, and in fact the ones we're going to be doing here are a directed graph. If you're not all that strong on this sort of thing, this is a great link for a free book, basically, It's an open source book of math, basically discrete math, which includes things like graphs. So I should have probably not clicked out of that, but here we are, we're back. And so you can see here I've embedded an image. That image is actually coming out of a GitHub account, and reasonably decent formatting. You can make it look prettier than this, but also notice over here the navigation happens in sync with this. So if we jump down to there, you can actually move through and navigate through your notebook and organize it. The way that these indentations are handled is based upon the level. So if you have a single pound sign, and this is a markdown thing, a single pound sign, it's like heading level 1, two pound signs heading level 2, and so on. So it's a pretty standardized sort of approach, but it's pretty powerful. So here what I'm doing is basically creating a data frame by reading from a table. And so this is kind of the inverse of what we did earlier of taking a data frame and writing it to a table. Here I'm creating a data frame from a table, a Databricks or a Delta table, or a Parquet table in this case. And what I'm doing, this command, again, doesn't really do anything unless I call display or something that makes it be collected or realized. So here you can see a list of classes in this table format. And this scenario here is that whenever you're taking college classes, there's typically prerequisites. And so modeling those classes as a graph, the prerequisites are the edges. So you need to have one class before you can take another is the basic idea. And so an odd thing with a graph frame, which is similar to GraphX inside of Databricks, is that you have to have certain columns in your data frame. And that's really the way it works, and we'll get there in a moment, is basically you give a constructor or a class instantiation to data frames, nodes and edges, and that's what constitutes the graph, and that allows you then to do graph algorithms on it. But those two data frames have to have certain names, and in particular the node has to be referred to as the ID. So the key that identifies the node has to be called ID. And similarly with edges, we're retrieving from the edges table, putting it into a data frame called E. Similar, it needs to be renamed so that instead of it being from and source, it's now to and destination. From becomes source, to becomes destination, so DST. And that with column renamed takes a data frame and changes the name of the column. In this case, the column that was from becomes source, the column that was to becomes DST. Understand though, a new data frame is created. It happens to be that I'm assigning it the same variable name of E. So I'm not really changing it, I'm creating a new one. And so here we can see same basic stuff, except the column headings have changed. So to create a graph frame, and we'll see if this works, is no more complex than basically saying import graph frames and then pass in the vectors and the edges, which are themselves data frames, and it gives you back an object, which is graph, a graph frame. You can then still access those edges and vertices that are the data frames that you just supplied it later on, and this means that you can do everything to these data frames as you would any other data frame, which is part of what makes it pretty compelling. So again, going into the concept, in order to take video game programming, you need to know how to do OO programming first, right? That's basic idea. So generally a base class will unlock multiple high-level classes. I don't have an entire curriculum in here, but it's enough to kind of make it interesting. So I'm using NetworkX here to do the plotting, and we'll see if this works. Oh, it did. A lot of times I have to go and actually install this stuff. So basically this is showing you, not in a real pretty way, essentially the relationship of the graph, and it's doing it in a kind of a spiral layout so that you can kind of see who points at what. You can also see there's some things out here that aren't all fully linked. Neo4j is a graphing environment that's been around for quite some time. This is the same data in it. It just does a better job showing it in a prettier graph I might could get the other one to look pretty good with time, but Neo4j is kind of natively done that way, so it does a really good job. So there's lots of graph algorithms that you might want to use, and again, a good discrete math text will share with you all the concept of graph theory, but there are some of these that, and that's kind of the point of using a graph library, is that it just natively knows how to do it, right? So triangle count basically counts the triangles in the graph. That's basically 3 nodes that have something to do with each other. So there's an arc between them one way or the other. There's also, sometimes you want to know things like the sum of all the edges at each one of the vertices, right? So how many things are ending with something. So how many things are pointing at each one of them. Similarly, how many things is each node pointing at? So the out degree, so which one is pointing out. And so you can see here, Introduction to Object-Oriented Programming, in this case, open up 5 different courses. So kind of an important class. There's also sometimes you just want to know the starting or ending. So there's a line pointing at it or coming from it. So which one has the highest cardinality of that? And in this case, you can see that Capstone 1 has the highest degree of the data that I put in. So one of the things we do have to do for some of these algorithms is use a checkpoint. What a checkpoint does is essentially allow the algorithm to make sure that it doesn't redo stuff. So it's a place to write things as it needs it. SC is the Spark context, and we're basically saying, here's the checkpoint directory you should use. We have to do that for this connected components, which basically returns back the things which are connected together. So there's kind of like the set of things that have something to do with each other. You can see it takes a little bit of time, so hence the reason that we need the checkpoint. And you can actually dig into what it's doing if you're so inclined to see the various stages that it's using and so on. And you can see there that it actually splits some stuff up into multiple jobs as well. And so we're going through, obviously, here on job 70, and you can kind of see what it's doing. You could also note here that it's set to 200 shuffle partitions. Probably not the best thing to do on this machine, but given it's a community edition, you can't necessarily tune greatly. All that really basically means is that it's going to default to thinking that it should shuffle things in groups of essentially 200. You want that to be typically a multiplier of the number of cores in your cluster, and it's kind of hard to get to 200 in a cluster unless you have a even number. Most things are by a factor of 4 anymore. So it's running through and basically figuring out the things that are connected. And then basically what we're going to get at the end of this is going to be those essentially kind of, it's not exactly clusters, but subgraphs maybe is a better way to do it, that they're connected together, and the number of nodes in each one of them is what we're doing. The nice thing here is that because we are generating a data frame as the output, we can actually down here actually do data frame related processing. So we take the results data frame, do a group by on the components, and order by the count, so we can see the one with the most highest. I'll go ahead and let that queue up. The community edition, as I think I mentioned, is a single node cluster. What that means is that there's one computer working as both the driver and the workers or worker. So not going to be very high performance, and that's part of what's taking so long here. In a true cluster, this doesn't take long at all because it's able to distribute that load across the cluster rather than having a single computer do it. And we can actually also take a look at what is going on that cluster by taking a look at the Spark UI, and also we can just pop out the the cluster's UI as well. And so basically we still are working, and likely at the point that we take a look at the cluster utilization, it'd be a nice shade of red because it's probably overly utilized. So inside of here we can take a look at the jobs that are running, and you can actually view, even though that particular job isn't expressed as an SQL job, right? This is Python, right? Not SQL. You can actually look at it from an SQL perspective and see what's going on. And we can see that the query is still running. We can go in and take a look at the running job ID and see what all's going on. And you can also see kind of what all it's been doing along the way. Likewise, we can take a look at the metrics so we can see what's going on with that cluster. Interestingly, it's not terribly pegged. So probably some other throttling going on because this is a shared environment and they're likely have us capped at a certain amount of utilization. So we're just kind of waiting for things to wrap up. If for some reason you want to stop, you can click on the cancel button, stop the execution of that particular clause, which is probably not a bad idea because we don't want to watch this. And again, the nice thing here is that you're looking at a totally web-driven interface. You don't have to log on to the server at all. So here we can get rid of the vertices that aren't connected to other things. That's something we would have seen by these components because there's some clusters essentially or nodes out there that aren't connected to anything. So we're able to remove the ones that are isolated, that aren't connected, and then here's what's left over. So we've removed those vertices that weren't connected to others. There's also this concept of strongly connected, and that's where one vertex is reachable by every other vertex. There aren't any in this graph, so if there were, there would be more than one. Right, so every vertex essentially is to itself is what that's basically saying. Breadth first search is a way of searching through the graph, and this is basically we're looking for something with the name ITSS 230 or ITSS 439, and it finds those two. And probably the best known graph algorithm is PageRank. It's what made Google. And so what it essentially does is let you know what nodes are important. And in this particular case, the capstones are the highest page rank, which makes sense. They are probably the most important, most connected in the sense that things are pointing directly or indirectly to them, because they have a lot of things that must be completed before you can take them. And you can also take a look at the weights that were calculated between the various sources and destinations. And because this is a data frame, I could actually join that to something that showed you something prettier than 25 and 21. And the concept of label propagation is that sometimes you want to have nodes that are closer together in a community sense, essentially come up with a class name. So it's almost like a clustering kind of concept, but you label those things that are essentially close to each other. Another thing that you'll sometimes do inside of graph is motif finding. That just means that you're looking for essentially a pattern or a shape to the graph. So a good example is checking for a node that has, or two nodes that are in a loop. So A points to B and B points to A. In this case, there are none. because there shouldn't be. Otherwise, you would have a class that you could never take because it depended upon a class that you had to take it. So that's kind of the idea. And this is also checking for 3 node loops. So A points to B, B points to C points to A. None of those as well. We can also just look for a chain of 2, something pointing to something. So A points to B. And there's quite a few of those, obviously. Then we can also do some, this is showing that because this is a data frame, everything we're dealing with is data frames, which is the first class construct in Spark. We can join using a select and essentially join things together in a nice clean way, changing the label of things so that it's a whole lot more readable. Also, this is showing that we're doing this dot notation is pulling out of this object. So this is actually an object, not just a string, just as this is. So we can see that it is an object with attributes. And we're using this dot notation to say, I want a dot type or a dot name. And that's what we're doing here, is literally turning it into, taking it from essentially an object construct to breaking it out into the various columns. Here's looking for a chain of 3. So A points to B, B points to C. And then you can take a look at what those labels might be, again, using that nice dot notation. Because you're getting back from that query a kind of, you can think of it as almost like a JSON, right? This is the JSON representation, but it's actually an object, in this case, essentially a dictionary, right, of name-value pairs. And then moving on up to the chain with 4, so A to P to C to D, and we can see that there are 9 of those. And then try to find 5, right? Is there 5? And there are 4 of them with 5, but is there 6? And this is speaking to the depth of the query, so figuring out what's kind of the long straw, if you were. So going back and looking, well, which one of these end with capstone 2? Hopefully they all do, right? Because that would be what you would be wanting to get through the program to do. So with that, we can see what are the various ways that you might get there with the courses that you might take. So that's an introduction to both Spark, the concepts of Databricks and data frames, RDD, and so on. Shifting back to our presentation, deliverable 4 is to solve basic data manipulation problems with Apache Spark. And you can use Scala or whatever. I don't particularly care. You work for that same international data clearinghouse company. You've serviced thousands of customers and so on. So your instructions is to write a simple script using Scala to list the top 20 companies and their locations contained in the Fortune 500 listing. You will report your findings in the white paper below. Feel free to use Databricks Community Edition for this if you're so inclined. You can also, if you want to instead, use Spark in the either a standalone version inside of Hadoop or Spark by itself, or you can use it in HD Insight, whatever you want to do. Just using Spark. Simplest is to use Databricks. Explain how Spark relies on RDD to work with a variety of operations. Explain how the DAG is used to monitor RDD calculations. Explain the advantages of Spark's in-memory processing capabilities over MapReduce. Provide a look at the underlying technology that provides Spark with these important capabilities. And using the script instructions in step 1, explain how easy it is to solve a problem using Scala. Include the screenshots of your script and the results, and a detailed overall explanation of your work. Scala is relatively straightforward, and if what you're doing is essentially a top, so you're limiting your result sets to 20, you're going to want the locations and I would assume that's the top based upon revenue, but it doesn't exactly say. So revenue is probably where you'd want to go. You could go head count, whatever it is, document, however it is you're rating them. Here's some pretty good links. The Towards Data Science is a pretty good one. 21 steps to get started with Apache Spark using Scala, and so on. If you need help writing a white paper and everything else. The rubrics, as always, you're going for the green column. Criterion 1 is a thorough appraisal of functional programming concepts within the context of Apache Spark. Rubric 2, thoroughly critique the operation of RDD in the context of Apache Spark. A thorough demonstration of applying filtering concepts, so that's where you're basically limiting it to the top N, 20 or whatever it is. And with that, if you have any questions, let me know. That's what I'm here for. Otherwise, stay safe, and we'll talk again soon.